Start. Excellent. Welcome. Thank you all for coming. Thank you all for finding this room. We hid it as well as we could, but you found it anyway. So congratulations. We're going to be doing Bayesian statistics today. I realize that door is open. I'll try to get that closed at some point, but we'll get started anyway. I've got a few things up here to take care of. One of them is you'll want to load up the web page, which the tiny URL is up there. And you should have a post-it note that I'm going to use in order to match you up for the programming part. When we start doing exercises, I'm going to have you work in pairs. And there are a couple of reasons I'm going to do that. One of them is to make this as socially uncomfortable for you as I can. Because I know this is really awful. I know you don't want to work with strangers. I know you would much rather do this on your own. But I'm going to try to persuade you to play along. One reason I want you to do that is not everybody was successfully able to get the install set up. So if I can pair you up and make sure that at least one in each pair has an environment, that'll help. We have all different levels of Python experience. So if I can pair you up and make sure that we've got at least someone in each group who's pretty solid with Python, that'll help a lot. The other is it's just me versus roughly 50 of you. So here's what I want you to do when we're working on exercises. If you're stuck, you work with your partner and see if you can get yourselves unstuck. If you're still stuck, you might want to pull in a neighbor and see if you can figure it out. And then if you're still stuck, call me, I'll come and help. But the nice thing is that at that point, it will be very efficient because I'll be talking to at least 2 equally confused people. And I should be able to help get you unconfused. So that's the plan. I'm going to get started with some things that don't require programming yet, and then I'm going to pair you up. But if you want to start, you should have a piece of paper. We can get one later if you don't. That's just going to be your way of walking around and hunting for a partner. You're going to put a check if you've successfully installed the code that I distributed, and it runs, and you should see a little display that gives you a little compliment for how smart you are. If you've successfully done that, give yourself a check. If you haven't got that, give yourself an X. And then give me a number indicating roughly your level of Python experience. And we're going to use that on a scale of 1 to 4. So that's the scale is up there. OK, so that's my plan. Let's get started with an introduction to Bayes' theorem first, and then we'll get to the Bayesian statistics in a couple of minutes, probably during the second hour. If you're following along on the web, I'm going to go to the thing that's labeled Part 1. Thank you so much. Please stand by. You all can go to Part 1 while I get more information about this error. All right. Part 1. Good so far. OK. So how many of you have seen Bayes' theorem in some other context before? OK, that's good. I will not spend a huge amount of time, but I do want to derive it, because one of the things that's so nice about this is that it doesn't take a lot to derive it. It comes from a straightforward derivation of probability theory, which is if you want to know the probability that 2 things are true, so I'm going to have 2 events, A and B. That's going to be equal to the probability of A happening times the probability that B happens. Or at least that's the naive version that you often learn first in a statistics class. This part so far is true if these 2 events are independent of each other. In other words, if knowing that A is true doesn't give you any information about B, then this would be the correct notation. But more often, we're going to be interested in events that are relevant to each other. In that case, we need this additional term, and that just says that if both things happen, one way it can happen is that A can be true, and then I need to figure out whether B is true given that A happened. All right? So an example of this is, let's say you don't know very much about me, and so you don't know whether I'm married, and you don't know whether I have kids. So I could give you partial information. I could tell you I'm married. Now let's say that that's A. And now I ask you, well, what's the probability that I'm married and I have kids? That's where this term comes in, because now what you have to figure out is, what's the chance of having kids given that you know about me that I'm married? And that's going to change the probabilities. My chance of having kids is higher given that I'm married. And it works the other way around too. I could have written the probability of B, and that's the case where I tell you first that I have kids, and then you figure out whether or not I'm married based on, or given the information that I have kids. And these two things are equal to each other. I could have done that derivation in either order, and you can see that there's some symmetry here, and it doesn't really matter whether I tell you A first, and then you check B, or whether I tell you B first, and then you check A. So given those two things, I can now pull out this term and solve for it just by dividing through by P of B. So I can get the conditional probability of A given B, which is going to be this divided by that. It's the probability of A times probability of B given A all over the probability of B. And that's Bayes' theorem. And this is one of the many theorems that makes me want to invent a time machine so that I can go back, invent this, and if I succeed, then the next thing I'll say is, and that's Downey's theorem. So this is, unfortunately, still, and the guy's name is Bayes, so it's Bayes apostrophe S, Bayes' theorem. Now, if things have gone according to plan, this should be sticky, and I should be able to peel it off and post it on the wall. All right. Where's some good wall space? We'll keep this one because we're going to need it. All right, that's part one. Part two, if you think of it in terms of A's and B's, it might not be all that meaningful to you. There's another version of this, which is sometimes called the diachronic interpretation of Bayes' theorem, which is to say, if you want to know what's the probability of my hypothesis, the probability of my hypothesis, given that I've seen some evidence. Now, I'm just going to write exactly the same thing, except by putting in H's and E's for hypothesis and evidence, I find that it means more to me. So let me write it out and we'll see how it sounds. Yeah, I didn't think that was going to work. So that's all that. This is the version of Bayes' theorem that's sometimes called the diachronic interpretation. Diachronic means through time, and what it suggests is that if you see some new evidence, you can update your belief in that hypothesis using this term on the right. And what it says is, this is what you believed before you saw the evidence. This is the likelihood of seeing that evidence if your hypothesis were correct, and this is the likelihood of that evidence under any circumstances at all. So these terms, this one is called the posterior. This is the prior, and this is the likelihood. This, unfortunately, has the least useful name of the bunch. It's usually just called the normalizing constant. And all you get from that is you've normalized that probability, and what it means is that your probabilities are now properly on the scale from 0 to 1. And we're going to play some games with this several times today. You can compute proper probabilities that are always between 0 and 1, or if you care more about the ratio of probabilities, then you can work with likelihoods, which are just unnormalized probabilities. If that didn't make sense yet, we're coming back to that several times. Correct. So just to repeat that if you couldn't hear, I'm talking about the likelihood of a result given a sequence of facts or a sequence of evidence that has arrived. And each time a new piece of evidence arrives, I'm going to take my old level of belief and update it by multiplying by that ratio. And that'll give me my new level of belief. Yes, so this is the foundation of a lot of inference. Yeah. Okay, so let me give an example of all this, which is the cookie problem. So this is actually an example that was on the Wikipedia page for Bayes' theorem for a while, but someone decided it wasn't a good example and took it away. But I like it. So the premise here is that you've got two bowls of cookies. Bowl 1 has 10 chocolate chip and 30 plain cookies. Bowl 2 has 20 of each. And someone comes along and picks one cookie out of a bowl, doesn't tell you which one. Oh, sorry, picks a bowl at random, and then picks one cookie out of that bowl. The cookie turns out to be, let me see, plain? Yes. Cookie turns out to be a plain cookie, so what's the probability that that cookie was selected from bowl number 1? Let me put that to you for a couple of minutes. See if you can figure out how to apply Bayes' theorem to solve this problem. For now, since I haven't put you in pairs yet, you can just work with whoever you're sitting near. Think about it for a couple of minutes, and then we'll go over it in just a second. If you're stuck and you're not sure how to get started, I've put a few hints up here. So I want to suggest one way of thinking about this, which is I always like to think about these hypotheses as a difference of opinion. So let's say everybody on this side of the room, you all believe H1. I want you to practice believing H1. You believe that that cookie came from bowl 1, and you all believe that the cookie came from bowl 2. And what we're trying to do in some sense is use evidence to have a useful debate between the two of you. Now initially, because of the way the question is set up, we know that the probability of H1 is 50%, and the probability of H2 is 50%. In this case, it explicitly says that Fred chose a bowl at random, so we can get these priors. These are the prior probabilities, a half each. And now the question is, if you want to argue for your position, how would you do it? So if you're on this side of the room and you believe H1, what's the evidence that you would cite? If you're trying to persuade them, what would you tell them? Right, there are more plain cookies in bowl 1 than bowl 2, and therefore? So there's a higher probability that the cookie came from bowl 1. So you're making an argument based on the likelihood of the evidence given the hypothesis. You're saying, if H1 is true, then what's the chance of getting a plain cookie? 3/4. If you really are drawing the cookie from bowl 1, then your chance of getting a plain cookie is 3/4. If you're really drawing from bowl 2, what's your chance of getting a plain cookie? 1/2. Those two values are really the crux of the matter. What you're saying is that the evidence that we saw, a plain cookie, is more likely to have occurred under hypothesis 1 than under hypothesis 2. So the people on this side of the room can point to those two numbers and say, in effect, this number is bigger than that one, and therefore H1 is more likely than H2. What Bayes' theorem allows us to do is say exactly how much more likely. So we're going to plug in what we have here, and we can do it for either H1 or H2. I'll do it for H1 just for simplicity. So now the probability of H1, now that we've seen that evidence, is the prior that we started with, which is 1/2, the likelihood, which is the probability of the evidence given H1, and now we have to figure out what's the probability of that evidence under any circumstances at all. Okay? So most of this is easy, and we just have one more slightly hard part to do. So this is the prior that we already figured out. That's 1/2. This is the likelihood that we just figured out there. That's the 3/4. And now there are a couple of different ways to think about the denominator. In this particular problem, it's kind of easy to get it directly, which is what's the probability of pulling a plain cookie from either bowl? In other words, if I just took the two bowls and combined them together, what would be the probability of getting a plain cookie? Is that 5/8? So we've got, let's see, there'd be a total of 40 cookies, 30 of which are plain. No, sorry, 50 of which are plain. So that's the 5/8. So here, so this is a case where we can get P of E directly. Let me show you the more general case if you weren't able to do it by observation. More generally, you can get P of E by just adding up all the ways that E could have happened. So it could be that H1 is true, and you saw that evidence under H1, or it could be that H2 is true, and you saw that evidence under H2. Okay. So if you're trying to figure out how could E have happened at all, we're just going to add up all the ways it could happen. And it could happen under H1 or H2, and this is how likely it is to happen. More generally, you're just going to add up all the hypotheses with the prior of that hypothesis and the probability of the evidence given that hypothesis. I hope it's not too much of a stretch of your mathematical capabilities to see that this is just the special case of that for two hypotheses. Okay. And so now plugging in the numbers that we got, we have 1/2, 3/4, and 5/8. And what does that work out to? Let me give you a second to do arithmetic. I think this is going to work out to 3/5. Three-fifths or 60%. Okay. And we always want to do a sanity check whenever we do math to make sure we haven't messed anything up. Does that make sense? Can you make an argument to me about why that seems to be about the right value? Yeah, so it's certainly related to the number of cookies. It seems to have gone at least in the right direction. So I think you're making a quantitative argument that it's the right number. Qualitatively, we can also convince ourselves it went up. My prior belief was 50-50. Now it's gone up to 60%. So it went up, but not a huge amount, because I didn't have a huge amount of evidence. And it's certainly still possible that H2 could be true.
So that number, that 60%, so what we're saying there is we are 60% confident that H1 is the correct hypothesis.
Correct. Yep.
So give it 100 tries, I'll get 60.
Yeah, if you ran this experiment in multiple universes, right? Yep. Good. Yes.
Quantitatively, it also makes a little bit more sense because there's less than 75, which is if there was only H1.
Interesting. Yeah, I'll buy that. Yeah, you can kind of bracket it by thinking about the extremes. Yep. Yep. Okay, that sounds good. All right. So I'm now going to give you two other problems for you to work on. So if you're confused about what I just did, this would be the time to ask. You feel like you're ready to take on another one? All right, you actually have your choice of two. Again, try to work with a neighbor, especially if you get stuck on anything. But if you scroll down, you'll see the M&M problem and the Elvis problem. The M&M problem is a straightforward extension of what we just did. So if you want to practice, you should do the M&M problem. The Elvis problem is, again, a straightforward implementation of Bayes' theorem, but there's a little bit of a twist to it. It's a little bit more like a brain teaser. So kick that around. Hi.
Okay, so if the audience asks you a question, can you repeat it
Ah,
back
yes.
to the rest of the audience and to us because we can't capture their audio?
Will do.
So, okay.
Hi. That gets me into the line of the projector. I know it's not great. Sorry about that. How many people are working on the M&M problem? Elvis problem? Much less popular. Okay. Apparently so. I should have changed the order. In that case, I'll do that. So if you're working productively, you can ignore me. If you're a little bit stuck, let me maybe help you get unstuck. One way to set this up is to have two hypotheses. Hypothesis A is that the yellow one came from the 1994 bag, green one came from the 96 bag. Hypothesis B is the other way around. The priors are equal, assuming that my friend, let me choose randomly. And now what I need to figure out is what's the probability of seeing what I saw under hypothesis A and vice versa for hypothesis B. And now I've got the situation I started with, which I have a combination of an A and B. I have two things to figure out. In this case, I think it's reasonable to assume that they are independent, that the color that I draw from one bag doesn't affect the color that I draw from the other bag. And so the chance of seeing yellow in 94 and green in 96 is, let's see, 94, yellow was 20, and green is 20. Did I get that right? Green in 96. So this is yellow in 94, green in 96. Well, it's exactly because they're sorry. The question was, why is the green M&M relevant if the two M&Ms are independent of each other? The fact that they're independent of each other is actually good. What that means is that they contribute separate information. Each of them contributes information on its own, and I can combine that information.
But I think the question is kind of similar to one. I mean, why do we even care about it? It's
Yep.
very similar to the cookie question in the fact that, okay,
Yep.
if he told me then he gave me 2 cookies, since it's not
Right.
like if I remove the yellow, again, they're independent. Why do we even care about green?
Right.
Is it just the fact that green gives us information, so we're going to...
Yes. Yeah, so every time we pull an M&M from a bag, that gives us some information about that bag. And one way of thinking about that is, what if I had pulled out a chartreuse M&M? Right? That would have given me very strong information that, well, in this case, that neither of these hypotheses could possibly be right. So every M&M contributes some information. I think one of the reasons intuitively it's a little bit hard to get that here is that each of them is really contributing a small amount of information. The green M&M could have come from either bag, and the likelihood ratio is fairly small. Same thing with the yellow one. But if we take them together, we get at least some information out of the two. Similarly, to get a yellow one from the 96 and green from 94, the probabilities would have been 14 and 10. Is that right? So a key thing to look at when you're looking at this, the ratio of those two values is the crucial piece of information. Before we started pulling M&Ms, we thought that these two hypotheses were equally likely. And now we've seen that actually the evidence is about 4 times more likely under hypothesis A than it was under hypothesis B. So which number do you think is mistaken? So this one is under hypothesis A. The yellow one came from 94 and the green one came from 96. He gives me 1 M&M from each bag. Yep. Good so far? Okay. So again, this ratio is about 4 to 1, which means that we expect the probability of A to increase. And now to figure out how much it increases by, I'm just going to plug in Bayes' theorem. Okay? Let's see. I think, if you don't mind, I will skip the math, the arithmetic. Yep. Yes. Yep, so to get the denominator, I'll do the same thing I did before, which is probability of A Okay? And the rest is arithmetic. We'll take a break between sessions, and if you like, I can do the math, and you can check your answer.
Can you repeat once more when you say probability of evidence for given A?
Mm-hmm.
What you're trying to do is the probability that the M&M is yellow 94 back and green is 96 back.
Right. Yep. So I was told that I drew one M&M from each bag. So the two possibilities are either I got the yellow one from 94 and the green from 96, or the other way around. Those are the only two ways it could happen. And then this comes in a straightforward way from the numbers you're given in the problem. Okay. Let's see. So I think I'm going to skip the Elvis question for now. We can come back to it later on. I want to do one more thing before we take our first break, which is to start talking about the PMF library that we're going to use for some of the programming exercises. Okay. So far we've been dealing with just two hypotheses at a time. What we're going to work our way up to is lots of hypotheses, and that's how we're going to do Bayesian statistics. In order to get there, we're going to use a library that I wrote which represents probability mass functions. So PMF is a probability mass function. And what it represents is a set of values that are possible. So we're going to start out thinking about dice. So if you roll a 6-sided die, the possible values that you can get from that are the numbers 1 through 6. And each of them has some probability of occurring. And what, roughly, for a fair die, is the probability for each of those values? 1/6. Okay? So this represents the probability mass function for that die. And every time I say PMF or probability mass function, what I mean is a mapping between the possible values and the probabilities for each of those values. So this is a value. And this is a probability. Okay. So if you're a Python programmer and you are asked to implement a probability mass function, you think to yourself, okay, I need a type that can map from a set of values to their probabilities. What built-in Python data structure might you select to represent this object? Python dictionary would be a fine choice. And in fact, that's what a probability mass function, the PMF library that I've provided, is pretty much a thin wrapper around a dictionary, with one source of confusion that will mess you up, which is that the keys in this dictionary are called... Yeah. Okay, so actually, to the degree that you can, don't think of this as a Python dictionary. Think of it as a new kind of object that you've never heard of before called a PMF. And what it does is it maps from values to probabilities. Okay? So what I want you to do is take a look at the module. You have already downloaded the code, so if you go into your code directory, you can look around. Or if you want to just follow that link, you can get both the code and the HTML page is the PyDoc for it. To get familiar with the library, what I'd like you to do is poke around, read the code, read the documentation, and answer those questions. So how do you make a PMF object? How do you modify a PMF object? And then you're going to write a function that takes two PMF objects and computes the probability that one of them is bigger than the other. Actually, let's do the first two questions first, and then we'll get to that third one. Hey.
Okay, so considering your topic other verifications of loss of data, and in like 3 of the questions you didn't repeat the answer or the question.
Yep.
So the first one you did. But we
Yes.
liked enough to prompt you.
Yes, I understand, and I will try to remember. Sometimes it's obvious from the answer what the question was, and in that case, I won't necessarily repeat it. But
Okay.
I appreciate the reminder, and I will try to remember.
But even in that case, like,
I got it. Thank you.
I was saying, even if you think the question is obvious, our viewers.
I understand.
think it's
I will try to remember.
Yes. Thank you very much.
I find odd about the normalized function is if you pass in a bunch of probabilities that don't add up to 1, I mean, that doesn't even make sense to me.
Right. Yeah, you have to do that when it makes sense.
Is that one of the situations where when you're in it, you know you're in it and it's okay?
We'll see some examples, and maybe I'll come back. So it's hard. That's a hard thing to answer in general.
Okay.
Good. Okay, a couple of things to see in this module. One is there are actually 2 classes that you get from this module. There's both hist and PMF. Hist is a histogram in the sense that it's a mapping from values to their frequencies. That is to say, how many times they occurred. So it's a count. One thing, if you're talking about statistics and you say frequency, you mean how often something happened. Don't think of a signal varying in time that has a pitch or a frequency. Totally different use of the word. So in that case, the right-hand side here would be integers. They would be counts. We're pretty much going to be working with PMFs today, so everything on the right-hand side will be probabilities. Okay? So looking over the modules, what ways did you discover for creating a new PMF object? Mm-hmm. Yes, so using the constructor, and what was the second one? And using a set member, right. So you can construct what is in effect an empty PMF, and then use set to start adding elements to it. You can also, there are some functions down at the bottom that you might not have seen for creating a PMF given a bunch of other stuff. So if I give you a dictionary, you can make a PMF out of that. If I give you a list of values, and this is the most common one, if I give you a list of values, you can make a PMF out of that. Okay? So you should have in the code that you downloaded a file named pmfexercise.py, and it should look something like that. And what this shows you is an example of making a PMF from a list. So this is the 6-sided die. The possible values are 1, 2, 3, 4, 5, 6. Each of them appears in that list the same number of times, so they get the same probability. And then it uses the items method to enumerate the value probability pairs and print them. Yep. Yes, good. Okay. All right. And then the other question I asked is, okay, so how do you modify a PMF object? You mentioned the set method. So if you want to add a value probability pair, you can use the set method. What else did you find? How do you modify PMFs? Right? There's normalize, there's inker. So normalize takes a set of values and their probabilities and makes the probabilities add up to 1. It finds the total probability, divides through. Okay? Yeah. Sorry? Yep, there's log in the XP, so you can apply transforms. We're not going to do any of that today, so you can ignore log in the XP. There's also inker, which increments the probability associated with a particular value, and mult, which multiplies the probability associated with a particular value. And those are the primary things we're going to use today. All right. Okay. Have you been able to run PMF exercise? All right. So now we're actually going to do some programming. And so now we really need to make the pairings of people. So if you have your sticky note, you should have written on it the check mark and the X mark and your number. If you don't have a sticky note, remind me what your name is? You have the last one? OK. If you don't have a sticky note, you can do some shopping anyway. What I'd like you to do is find a partner to work with so that between the two of you, you've got at least one working environment where you can run the intro code. And you have at least someone with a 3 or a 4 on the Python scale. Well, I'll put the Python scale back up there. Okay. Are you working together? Yeah. And have you got a working environment between the two of you? Oh, no problem. Great. You guys working together?
Could, although if anybody needs a floor, I'm available.
Got it?
It seems to me that it should be the 1s and 2s should be seeking out the 3s and 4s.
Probably. Let me see how the rest of the pairing is looking. Good. So if you would be brave and stand up. Anybody not have a partner? If you'll stand up, that'll make it easier for you all to spot each other. We need somebody here, and you might end up having to move in order to make this work. Are you happily married? Have you have at least one working environment? So pair. Good so far. All right. Right. Okay, and you need somebody? Yeah. Okay, so let's see. How about if maybe the two of you, if you move up to the front row, I think there's going to be room up there. And either of you.
All 3 of us, is that okay?
Well, it looks like I have an odd number. So can I ask you, would you move up front and see if you guys make a good pair?
No, because I need the juice.
Oh, okay. Are either of you mobile? Would you mind?
Sorry, when you say mobile, like no.
Oh, I see. Okay. Let me see. Let's see if there's power up there. Let's see. You need power? I think you have power. Oh, okay. Good. Yes, good idea. Would you go and join them? Excellent. All right. Okay. Anybody left not have a pair? Okay, let me suggest the first thing you should try to do is make sure that you can run PMF exercise. Second thing is prob bigger. And then the third is that last question that was up there. If I roll a 6-sided die and a 10-sided die, what's the probability that I get a bigger number on the 10-sided die?
Prop bigger. Right now, it's just creating a new PMF. Because there's like stuff right
Hey. So I see some gesturing and conversation. I'm not sure of whether you're trying to talk to me or to each other. Very good. Okay.
We'll borrow a piece of your paper and hold up the sign.
Sounds good.
Well, obviously it only makes sense for
And my incentive program is that when we get this working, we get to take a break. Hey. Sure. Yes. We can take a stab at it now.
Okay. We have the individual piece of E, A,
Mhm.
and EB.
Yep.
How do you combine them with Bayes theorem?
Sure. Let's see.
Just calculate Bayes individually for both of them and then multiply the two together. Is what I'm guessing.
You don't have to multiply them together. You'll compute them separately. The only place where they come together is that they're both going to have the same denominator. But other than that, you can compute them separately, and then you'll see conveniently that they add up to 1, because they kind of have to. Hi. Hi. Okay, if you're making good progress without me, then feel free to ignore me. If it would be helpful for me to get you unstuck, let me make a couple of suggestions here. So I gave you an outline of prob bigger that creates the PMF object, and then I think in the version that I gave you, all it does is return that PMF object. So it's empty and kind of useless. Okay, so your job is to fill in the middle of that function. Here's what the general shape of that function is going to look like. You're going to enumerate all the values from PMF1, all the values from PMF2, and now you've got all pairs. And for every pair, you know the probability of that pair. And so, oh, sorry, I called the result res just because I had too many things named PMF in that function, and it was starting to make my head hurt. Okay. And then to test it, I've created a PMF that represents the outcome of a 6-sided die. This PMF represents the outcome of a 10-sided die. And now I just put that in to do some error checking. And now I'll see if I can compute the probability. So you can get back to work, I'll get back to work, and I'll check back in just a couple of minutes. Sorry, I got myself confused there, and I might have confused you. This thing is going to return a floating point value, not a new PMF object. You probably knew that. I probably just messed you up. Sure.
What are you trying to do? Like the value of PMF1 of this is greater than the value of 2. Then we're trying to sum the probabilities?
Right.
The product of the probabilities?
Yep.
So what's the rationale behind it? I'm kind of
So I'm enumerating all the pairs, and for each pair I know the probability of getting that particular outcome. And
because they're mutually exclusive, that's why you're
and they're not only mutually exclusive, they are also collectively exhaustive. Because they're the only possibilities, and they add up to 1. And so actually that's the question I was going to ask, is whether I have to do any normalization. And the answer is no, it works out just right.
what will the total reflect finally?
That'll be the total probability of all the pairs where the first one is bigger.
We're not applying any base term or anything right now.
Not yet. Not yet. You don't have a partner? After the break, I'll try to get you paired up with somebody. Were you able to get the environment installed? Oh, okay, good. Sure. Yep. Well, we have an odd number of people. You're on your own, at least for now. Okay, so I'd like to go over a solution, and then if you have questions, we can do those, and then we'll take a break, and we'll get into the second part and really do some statistics. So the function I've written up there enumerates all the possible pairs. So in the inner loop there, the V1 and V2 are all the pairs, and the probabilities P1 and P2 are the probability of getting that pair. If I multiply P1 by P2, that's the probability of getting that pair. And so now all I have to do is count up all the pairs where V1 is bigger than V2 and add up the total probability of those pairs. That making sense? Is there a question about it? Sure. So each time I go through that inner loop, I've got a pair of values, V1 and V2. And I'd like to know what's the probability of getting that pair of values. So the probability of getting that pair of values is P1 times P2. Okay. And now I want to know what's the total probability of all the pairs that have that property. Okay. And that's what I'm going to get by running the loop. Good so far? All right. We'll take a break. If you have questions you want to ask me during the break, we can do that. We will resume. I've got 10:05 on my watch. Let's resume at 10:10, so 5 minutes. Okay, we should get started for part 2. So if you load up part 2 of the web page, you'll be treated to the profile of the King of Belgium, who is on the Belgian euro coin. And it's the premise of the second question that we'll be working with for a little while, which is whether or not euro coins are biased when you spin them on edge and let them fall over. Now, one of the things when people talk about coin tosses, at least in the States, conventional coin toss methodology is to flip it in the air so that it's spinning in the air and then either catch it or let it hit the ground. And for that, mostly any coin is going to be pretty close to fair. But when you spin a coin on edge and let it fall over, it's at least plausible that you're going to get more heads than tails depending on how that coin is weighted. And particularly in this case, the profile, if you look at this coin edge on, the profile is raised and the tail side is flatter. So it's at least plausible that you're not going to get a 50-50 coin out of this. And this was a topic of great discussion when the euro coins were first introduced. In fact, this was a newspaper article. Now, I have to give 2 levels of citation for this. This was a newspaper article that was cited by David Mackay in his book, which I'm going to recommend to you anyway. It's the book where I first got exposed to Bayesian statistics. I think it's a really great book. It has not just Bayesian statistics, but a lot of other interesting topics too. It also is available free on his webpage. So if you follow that link, maybe I'm not sure if that's a link, but if you Google around for it, you can read his book. But in the meantime, here's the question that he posed. They said when the coin came out, somebody did the experiment. They spun it on edge 250 times. They got 140 heads and 110 tails. And they took that to a statistician, Barry Blight, lecturer at the London School of Economics. And he said if the coin were unbiased, the chance of getting a result as extreme as that would be 7%, which is fairly low. What he's implicitly doing there is a classical hypothesis test. So if you're familiar with classical or frequentist statistics, that's what they're applying there. And the argument that he's making is that those results would be unlikely if the coin were fair, and therefore it serves as evidence that the coin is unfair. What we're going to do is the Bayesian analysis of that claim, and I'll give away the punchline right from the start, which is, first of all, we're going to need to do some work to formulate the question more precisely, but once we do, we'll find that this is possibly weak evidence in favor of the coin being fair. So we're going to come to the opposite conclusion of what the frequentist statistician claims here. But it'll take us a little while to get there. The first thing that I want to do is a live demo of Bayesian estimation. And we saw a version of this morning when we had this side of the room believed H1 and this side of the room believed H2. We're going to do something similar about the Belgian euro. which is that we have a room full of people, and you all have different hypotheses about this coin. And so what we'll do is you're going to start with a prior, and you're each going to start with a different prior, and then we're going to accumulate evidence. And as we accumulate evidence, you're going to update your priors, so that at the end, you as a room full of people will now have a suite of hypotheses with a probability associated with each one, and that's going to represent collectively our posterior belief about this coin. All right, so that's the plan. Let me go through that one step at a time, and hopefully it will be clearer. So first thing I'll do is, let's say I have my imaginary Belgian euro coin here. You can think of P, the probability of getting heads, as being some physical characteristic of this coin. So the fact that it's a probability might get a little bit confusing in a minute, but just think of it as a physical characteristic. So this coin has a height and a weight and some value P that we don't know yet, which is its probability of yielding heads. Okay? Now, you all have a different belief about P. I want to start out with what is, in a sense, the least informative prior belief about P, which is that it could be uniformly distributed between 0 and 1. All right? So what I want you to do is either use the Python random number generator or use the random number generator in your head, whichever you prefer, to pick a random number between 0 and 1. I'll give you a second to do that. All right. When we start out, you are all going to be equally confident of your hypothesis. So I'm going to give you all 1,000 points of confidence. You might want to write that down, because that's going to be your bank account while we do this exercise. So you all have different values. So how many of you have a value that's less than 50%? And how many of you have a value that's more than 50%? Good. So it's roughly 50-50, so you've done the first part of the exercise correctly. All right. So if I now draw a graph of all your different beliefs about P and the confidence that you have in that belief about P, I'm going to get something that looks like this. I don't know that they're going to be perfectly equally spaced, but I'm going to draw them that way just for simplicity. Okay? And you all have the same amount of confidence. So that's where we are when we begin. You each individually have 1,000 units of confidence. So the total is roughly 50 times 1,000 points of confidence. Virtual confidence. Good. Okay. So now I'm going to give you some evidence, which is I'm going to flip my imaginary Belgian euro coin. And it came up heads. Actually, I suppose I should have spun it on edge to do this correctly. Came up heads. And so now the question is, how should you update your degree of confidence based on what you just saw? Now, one way to think about this is intuitively, which is who had the lowest value of P? Did anybody pick 0? No? How about 5% or less? Okay. So if you thought that heads was extremely unlikely, 5% or less, and the first toss of the coin came up heads, how confident do you feel now about your hypothesis? Not so great, right? How about anybody at 95% or higher? Okay, so I tossed a coin, I got heads, just what you were expecting. So how much effect is that going to have on your level of confidence? Not a lot. You still feel pretty good about it. All right, so let's now take that intuition and do it more mathematically. Think about this from the point of view of Bayes' theorem. So your belief about your hypothesis, having seen that evidence, is going to be proportional to how much did you believe it before? How likely was the evidence if you were right? And how likely was the evidence under any circumstances at all? Now, I'm going to do a little bit of a cheat here, which is I'm not going to bother to figure out the denominator. In some sense, everyone in the room is going to help me keep track of the denominator, because all I really need for the denominator is how much is the total confidence in the whole room. So I'm going to skip the math on the denominator, and we're just going to do this update. Okay? So the update you're going to do is that your confidence after each coin flip is going to be your confidence before the coin flip times the probability of the evidence if your hypothesis were right. Okay? So you all hold a belief about P. So what's your value for P? 0.79. So you believe that heads occurs with probability 0.79. So what's the probability of getting heads under your hypothesis? 0.79. I'll play that game one more time just for fun. So what's your value of P? 0.12? 0.12. So you think that heads is going to come up 0.12% of the time. So if I flip heads, what's the probability of that evidence under your hypothesis? 0.12. Sorry, it's a trick question that makes you think that can't possibly be right, but that's the case. So for every single one of you, whatever you believe about P, that's what you believe that this is. In other words, this term is exactly P for heads. So if you see heads, then the probability of that evidence, given your hypothesis, is P. What about tails? What if I had flipped tails? 1 minus P. Each of you believes that the probability of tails is 1 minus P. So what happens now if I draw that graph again? So I started out with that graph. Everybody had the same amount of confidence. I flipped heads. So after seeing 1 heads, let me not use H for heads because that'll be really confusing. I flipped 1 heads, and now one. If you thought that heads was impossible, how much confidence have you got left at this point? Your confidence is gone. If you thought heads was 1, you haven't seen anything the least bit surprising. So you've got just as much confidence as you started with. What does the function look like in between those 2 points? It's just a straight line, right? So you took your confidence and multiplied it by P. So if I now plot this curve for the whole room, I've got a straight line between 0 and 1. Okay? The question is this why in statistics it's important to have a large sample set? The answer is yes. This is an example of, I've only seen 1 coin flip. I can't really draw a strong conclusion from it. And in fact, even these really low hypotheses, I haven't drawn that clearly, but there's still some chance that that's right. But one nice thing about this method is that having seen 1 coin toss, I can tell you exactly what we should believe about that coin on the basis of that evidence. Okay? Yes, please. Right. If you had 0 confidence before, then it's going to be 0. If I had tossed heads, you would have been multiplying by 1. So you're right. The 2 hypotheses on the end, the 0 and the 1, those are in some sense the most dangerous hypotheses to hold, because it's very possible that you will be contradicted by the evidence and your confidence will go to 0. Everybody else, your confidence won't go to 0 no matter how much evidence I show you. Okay? Let's do one more. So let's say I flip the coin again and I get heads again. So I want you all to do the same update again. So take your confidence before, multiply it by your value for P, and then you're going to get a new confidence after. You started, so your initial confidence was 1,000. Yes, so for this one, all I cared about is that we all started out equal, and we're all going to do the same update, and then when we're done at the end, I'm going to normalize by dividing through by the total amount of confidence that's left. Yeah. Heads again. So far we've seen heads. And so the amount of confidence that you now have left is the 1,000 points of confidence that you started with, and then you multiplied it by P when I tossed the first heads, and then you multiplied it by P again when I tossed the second heads. So let's see how we're doing here. I had somebody who picked a really low value for P. I forget who that was. Who had the low P? What was your value for P? So, 0.026. Oh, 0.2. How much confidence have you got left? It's all right. It's going to be about 4. I think you've got 4 points left. So you started with 1,000 points of confidence. You've only got 4 points left. How about a nice high value? Somebody put 0.95? 0.84? Who's got better than 0.84? You still have 885 points of confidence left. And how about somebody near 50%? 0.46, and how many points have you got left? 211 points left. And what does that curve look like in between? Hint? Parabola. Yeah. Notice how I didn't actually hit any of the points. Nevertheless, so now we have a curve that looks like this. So the low values of P are becoming less and less confident. High values of P are feeling better and better about their hypothesis. Let me do one more just to see what happens now when I toss tails. So let's try it again, totally random, no idea what's going to come up. It's tails. So we're going to do one more calculation. We've now seen heads, heads, tails, 0, 1, P. So 2 things I'd like you to do. First of all, figure out your new value of confidence, and then sketch what you think this curve is going to look like. If you're not sure how to compute your confidence, here's what it is. You started with 1,000 points. You multiplied by P once for each time we see heads. You multiply by 1 minus P for each time we see tails. So this is what the overall shape of the curve looks like. And now we can plot a couple of points. So the hypothesis P equals 0 has been contradicted at this point. How about the hypothesis that P equals 1? also contradicted. So this curve now is 0 at both of those points, and in between, it's going to look something like that. I didn't get that quite right, because we should talk about where's the highest point there. So who in the room has the highest confidence left? Anybody have a bid? I hear a theory that it's going to be near 2/3. I'd like to see how it works out by the numbers. So anybody have 300 points of confidence left? 200? 100? Ah, okay. How about 150? 160? 155? All right, the 150s, what are your values for P? 0.7? 0.48, and that comes out, okay, yeah, yeah, 0.7, 0.48, 0.63, yeah. So 0.63 is probably doing quite well at this point, because we've seen 2 heads and 1 tail, so if we really had to just pick one value and make a guess, we would guess 2/3. And in fact, the high point of this curve is at 2/3. Okay? So if we just had to pick a single value, that's all we would have to do, and it would be easy. The nice thing about this curve is that it tells us not only the most likely outcome, but also how strongly we should feel about it. That the width of that is a measure of how uncertain we are about P. And one of the ways to quantify that is to now find brackets there that contain, let's say, 90% of the confidence in the room. Yeah?
I guess instinctively, the person who would have 2/3 should have all this confidence.
Ah, good question. So the question is, the person who has 2/3 should have all of their confidence left. And that is one part of this that's a little bit weird, which is that everybody's confidence is going down, whether you're right or wrong. You win if your confidence goes down slower than everybody else. Okay, so your relative amount of confidence to other people, that's the important part. Your absolute amount of confidence doesn't really matter. And so in fact, the probability that you are exactly right is quite small, and that's the reason that your confidence keeps going down. But the probability that you're at least close to being right is good, and again, this curve is going to let us be quantitative about how to figure that out. Okay? All right. So we've done this by being a big computer in a room. We've sort of been, we've been the distributed or parallel implementation of a Bayesian estimation. But that's what we've done here, is we've estimated the value of P using the evidence that we were shown. What I now want to show you is coin.py, which is one of the examples that you were given, is the code that does exactly what we just did programmatically. So if you bring up your copy, I'll bring up my copy, and we can go through that. Okay. So the first function up here is called makeUniformSuite. I'm using suite as a synonym for set. So you have a set of hypotheses. And what I mean by a suite is, for each hypothesis, I have a probability associated with it. Or another way of saying that is the confidence associated with it. So makeUniformSuite creates a PMF object that maps from a hypothesis to my degree of confidence in that hypothesis. Can I give an example? So this is the example that we just did. So you can think of each one of you is one of these hypotheses, and the right-hand side is your level of confidence. Okay, so I'm starting out with a room full of people who all have different values of P, and they all have the same amount of confidence. And now I want to do an update. Here's what the update looks like. It says I'm going to loop through all the hypotheses in the suite. And for each one, I'm going to compute the likelihood of that hypothesis, sorry, the likelihood of the evidence, if that hypothesis is correct. And I'm going to multiply the confidence by that likelihood. So this is exactly the computation that you guys just did in person. We just have it as a loop rather than a room full of people. And then when I'm done, I'm going to normalize all the confidences so that they add up to 1. And I think this is getting at the question that you were asking, which is everybody's confidence is going down. But now when I normalize it, that's going to cause some to go up and some down. Right? Okay. And then the last piece is that I have to compute the likelihood of the evidence given that the hypothesis is correct. Now here's where I'm just going to unpack those data structures. The evidence is a tuple that just contains the number of heads and the number of tails. And the hypothesis is just P, the value that you believe for the coin. And that's it. That's pretty much what the whole thing looks like. So now the structure of the computation is, I'm going to start with a uniform suite. I'm going to start with the evidence that I was given, which is 140 heads and 110 tails. I'm going to do an update on the basis of that evidence, and then I'm going to plot the resulting PMF. So let's take a look at that. What do you think of that? So a couple. This is the probability of H given E, right, for each of the hypotheses. So this is the person who believed that P was 0, and that person has been disappointed. Similarly, the person who believed P equals 1 also has no confidence left. And in fact, if you believed anything less than 0.4 or anything greater than about 0.7, you have been all but contradicted. Now, those are not quite 0. If you zoom in there, there is a little bit of value there. So it's possible that those are correct, but extremely unlikely. All of the likely values are between about 0.5 and about 0.65. And the most likely value is the 0.56, if I remember right. That is the actual observed rate of heads, the 140 out of 250. Okay? So that's the posterior distribution for P. We started out thinking that P was equally likely to be any value between 0 and 1. And then we did an update. And now this represents the posterior belief about P having seen that evidence. Good so far? All right. Let me close that. Now, so the second exercise is coinexercise.py. If you open up the file, you should see this starting code. This is what we're going to use to answer the question that Mackay posed, which is he said, having seen this evidence, 140 heads and 110 tails, what's the probability that the coin is fair, and what's the probability that the coin is biased? Now, one of those is straightforward to figure out. If you want to know the likelihood, the probability of the evidence, given that the coin is fair, we can do that, okay? Because the coin is fair means P equals 50%. And the evidence is, again, 140 heads and 110 tails. So what is the probability of getting this outcome if we know for sure that P is 0.5? Anybody feeling brave?
Very, 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 very small.
Very small. It's true, actually. Any outcome is quite small. It's going to be proportional to p raised to the 140 and 1 minus p raised to the 110, which is exactly the likelihood we just computed. So sorry, I need to flip back and forth between coin.py. If you look inside coin.py, you look at that likelihood function. This is exactly what it's doing. If you tell me what p is, and you tell me how many heads and how many tails you got, I'm going to compute p raised to that number of heads, and 1 minus p raised to the number of tails. Okay. Now, to do that right, there's one other term that should go there, which is the binomial term. But for the same reason that I'm not going to do the normalization yet, I'm also going to ignore that term, because that's going to be constant for all the hypotheses. It doesn't depend on p, so I'm going to leave it out. I'll ask you to take that on faith for now, and if you want, we can go back and I'll show that more clearly. Okay? So it's straightforward to compute the probability of the evidence if the coin is fair. The problem is, how do we interpret the coin is biased? So what does that mean to you? And one way of thinking about these kinds of inference problems is to think about a barroom bet. So if you make a bet with somebody, you have to do some work to formalize it, to get it down to a sufficiently detailed description that you guys can agree on who won the bet and who lost. So if you say, I think the coin is fair, and again, I'll give you guys that hypothesis. You guys think the coin is fair. It's really easy to make that precise. That means 50-50. All right? You guys think the coin is biased. What does that mean to you? And this really is an open-ended question. How do you interpret that phrase in English and try to make it into a formal description? So one possibility is anything that's not 50-50. Right. So your suggestion is, if all I know is that it's not 50-50, I don't really know very much about it at all. Yeah. Any other thoughts?
Even with a fair coin, you're going to get differences when you actually do tosses. So it's got to be like a threshold that you've got confidence in.
Right. So even with a fair coin, I'm going to see variability. That means if I run any finite experiment, I'm not going to get exactly p. Right, so I do have to account for that. Although for now, let's just think about p as being a physical quantity. So I don't know what it is exactly, but I just think of it as being a fixed value, at least for now. Okay. Yep. Yep. Right. Yeah, so unless the coin is designed to be perfectly balanced, it's in some sense never going to be perfectly fair. There's always going to be some variability. So you've got a notion there that this hypothesis, the hypothesis that the coin is fair, is in some sense trivially false for any physical coin. Nothing is perfect, so it's never going to be perfectly 50-50. Right. So this, I think, is a good discussion because it's getting at exactly what makes this problem tricky, which is that we need to be precise about what we mean by both hypotheses. Now, if you'll let me get away with this one, so I want to compare two sort of abstracted hypotheses. So I'm not going to get quite down to the level of looking at the molecules of metal and the perfect balance and all that. But if I just wanted to compare two hypotheses, so one of them is, I know that the coin is 50-50. The other one is, I know that it's biased, but I'm not sure which way. And now there are a couple of ways that we could do that. And one of them is we could say, look, I'm not sure. P might be 0.6, and P might be 0.4. And let's say it's a 50-50 shot between the two of those. Now, that might not be the right way to do it, but the reason I want to start with this is that I can answer this question. So if this is B for biased, Okay? I can answer the question, what's the probability of the evidence given B? And that's because I've got two sub-hypotheses. So if B is true, then one of these two is true. And so I can compute 1/2 of P of E given plus E given 4. Look, right. So if this is 50-50. This is 50-50, and so that's where those halves came in. And sorry about the notation, which could be a little bit confusing. The capital P is a probability, and the lowercase p is what I believe about that coin. Okay. And so now the chance that B is true is the sum of the two ways that B might be true. That's where that comes from. Okay. Let me try to make this concrete by doing the exercise. So if you look at coin.py, what it asks you to do is compute the probability of the evidence given B. And I'll give you a head start. I'll give you the evidence, and then here's how we're going to compute the likelihood. So if the coin is fair, then P is 0.5. And so this is the likelihood of the evidence if the coin is fair. And I want you to compute all right, if you don't want to know the answer, don't look up here. I'll give you a couple of seconds to work on that. Hang on just one second. Somebody had it. Right.
So if you feel like there's more weight, I mean, if you look at the data, that wouldn't be necessarily 50-50.
Right. Good.
At what point can you use the data that was conducted to sway where your bias would be?
Good question. Right. So the way I formulated this hypothesis is I said it's either higher or lower, and I don't know which. And your point is, well, wait a minute. When I look at that data and I see more heads than tails, that makes me think that this is more likely. But I think you're rightly thinking, well, wait a minute. That's a little bit of a cheat because I used the data to formulate my hypothesis, and now I'm going to use the data again to decide which hypothesis is correct. And your intuition there is exactly right, which is you're not allowed to use the data to formulate your hypotheses. You have to, when you define what B is, do it using honest information that you have prior to seeing the data. So for example, it would be fair, if you know something about coins, it would be fair to use that information. But looking at this particular data set would not be legitimate.
If there was another data set out there that
Yep. Correct. So the question was, if there's another data set out there, can I use that and then use this data set to do an update? And the answer is yes. In fact, in general, you can take any sequence of data and split it up any way you want. So you can think of their data set as your way of computing your prior belief, and then you do an update with the new data, or you can treat the whole thing as one unit of data. Bayesian updates come out the same way, regardless of how you group the data.
I think I was wondering who said to that on the difference between probability and likelihood.
Good question. So the question, what's the difference between a probability and a likelihood? They get used in different contexts, but in this context, a likelihood is a probability that I haven't normalized. Okay, and so what that allows me to do is computationally, I get to do some cheating, because there are a bunch of things I don't have to bother figuring out. And so let's take a look at the code I've got up there. So this says I'm going to compute the likelihood of the evidence if p is 0.4, the likelihood of the evidence if p is 0.6, and then I'm just going to average them together. And so that's going to give me the total likelihood of the hypothesis that the coin is biased, at least by this definition of biased. And what I get are these two very small numbers, roughly 5 times 10 to the minus 76, and 7 times 10 to the minus 76. And this is consistent with what someone said a minute ago, which is that all of these numbers are very small because the likelihood of any specific outcome is always quite small, but what I really care about is the ratio between those two things. So based on those two values, what conclusion would you draw about these two hypotheses? Correct. Based on this, we would say, if the coin is fair, this is the probability of seeing what I saw. If the coin is biased, it's a little bit higher. And since the outcome is more likely from a biased coin, I would say that this evidence serves as support for the hypothesis that it's biased. In this case, it's quite weak support because it's roughly 7 to 5 or 7 to 5.5, so it's only slightly more likely. But if we interpret the biased hypothesis in this way, then the evidence supports the biased hypothesis. The ratio is significant. You're right. It can get as small as you want it to. And in fact, when I'm comparing just two hypotheses, when I now do the Bayesian update, let me see if I still have my Bayes theorem handy. Here we go. So you're right, when I look at the numerators, they're all going to be very small because the probability of the hypothesis given the evidence, sorry, other way around. The likelihoods are very small, but the denominators are also very small. Yep. This is only treating two hypotheses. It's treating either this coin is fair, or this coin is biased in this particular sense of biased. So I'm ignoring all the other hypotheses. Right. And that's, in fact, the next step that I wanted to take is we can generalize B a little bit. It would be funny to say about a coin, I know that it's exactly 0.4 or it's exactly 0.6, but I don't know which. It would be much more likely to say, I think there's a range of values that it falls in, and I don't know exactly where it is in that range. And I think that's getting at your question. Okay, so let's do that as the next step. Rather than just have two ideas about what P might be, we're going to reformulate B. Every time I go to the podium, I take a pen with me. I started with 4 pens. Now they were all up there. Now I can restart. So we're going to reformulate B. B is still the hypothesis that the coin is biased. Except now what I mean by that is I think it's anywhere between 0 and 1 and uniformly distributed. Okay. Now, if you want, you can cut out a little notch in the middle and say, except 0.5. But it turns out that as the number of these hypotheses increases, it matters less and less about whether you actually exclude 0.5. So really, the two hypotheses that we're going to compare here are... Oh, I shouldn't have drawn those verticals, because rats. So fair is the hypothesis that p is exactly 0.5. Biased is anywhere from 0 to 1, and I don't know where. And now I'm going to do exactly the same thing that you did there, except I'm going to do it for a larger number of hypotheses, and that's in coin2.pi. So if you take a look at that, so the key function here is integrate likelihood. And what it does is it creates, well, it actually takes a suite of hypotheses. This is what do you believe the value of p is. It computes the likelihood of each hypothesis, and then it just adds up those likelihoods. Now that term might look familiar. What I'm computing there is the summation that I had several sheets ago. Where's my summation? There it is. This was the probability of the evidence is the summation of all the ways it can happen. I'm going to loop through all the hypotheses and multiply together my prior belief about that hypothesis and the probability of the evidence given that hypothesis. That's what that loop is computing.
The probability of each hypothesis is still the same.
Yes. And so in this example, these are all the same because I started with a uniform distribution. And so I could leave it out. Okay, if you run that program, you should get the two likelihoods and their ratio. So what's your interpretation of that result? It says that under the biased hypothesis, the likelihood is about 2 times 10 to the minus 76. Under the fair hypothesis, it's about 5 times 10 to the minus 76. And the ratio between them is about a half. So what does that mean to you? Can't draw a strong conclusion one way or the other, because the likelihood ratio is only 2 to 1, which is fairly weak kind of evidence. I agree with that. But which way does the evidence lean? Leans toward it being fair. If you had to interpret this result, you would say it's about twice as likely that we would see this outcome if the coin is fair than if it's biased, at least for this definition of biased. Okay, so if when you say biased, you mean I have no idea what p is. It could be anything between 0 and 1, and I would be equally unsurprised by any of those values. If that's your hypothesis, then this data does not strongly support that hypothesis. Okay? Any questions about any of that? Yes. Right. So this is a case where what you mean by biased changes the conclusion that you come to. And that's a good general warning to be aware of, which is that often, lots of real-world problems, you have to do some work to get it from a vague description down to something that's formulated quantifiably, and then how you do that is going to affect the result. Now, one way to interpret that here is to say, this is not strong evidence one way or the other, and therefore how you formulate the problem makes a big difference. There are other cases where when the evidence is very strong, it's not going to matter quite. You don't have to be quite so careful because you're going to get the right answer anyway. But that's a good way of summarizing this example. All right, you have earned your second break. So I've got 11 o'clock on the nose. We'll start up again at 11:05, or how about 11:07? We should get started again. The end is in sight. We have only one more problem to work on, which is the SAT problem. And I'm going to try to get this out to you guys to do a little bit more work on your own, so I'm not doing quite so much standing up here and talking. Let me pose the question. So here's the scenario. Alice and Bob are having a conversation. Alice says, what did you get on the math SAT? And Bob says, 760. And Alice says, oh, well, I got a 780. I guess that means I'm smarter than you. And the question that we're going to answer is Alice really smarter than Bob, and what's the probability that she is smarter than Bob? So again, we need to do some work to formulate this in a way that we can quantify. So let me start by saying that by smarter, all I'm going to mean is better at answering SAT questions. Nothing more or less than that. And so what I want to know is, what's the probability that Bob correctly answers a randomly chosen SAT question? What's the probability that Alice correctly answers? And then we can answer the question of whose P, in this case, is bigger. Okay? All right. So again, I'm going to assume that each person has some probability P of answering a question correctly. And now we're going to figure out how to do this update, which is I need some prior distribution for P, and then I'm going to use the evidence to update it, and then compare the posterior distributions. And we need some data, which fortunately the nice people at the College Board provide for us. So they've given us, at least for 2010, the scale, which is the mapping from your raw score, how many questions did you get correct, to the scaled score, which is the from 200 to 800 range that people are familiar with. And so I've put that data into a couple of CSV files that are in the directory that you downloaded. And I've provided this block of code, which creates an exam object. And if you want, you can look through the code and get a sense of what that does. But what it represents is the data from the College Board and a couple of functions that are going to do some interpolation for us. So if we know Alice's scaled score is 780, we can look that up and map it onto a raw score. The exam function provides a method called getRawScore that takes the scaled score and returns the number of questions that Alice got correct. Okay. And it also gives us the prior distribution, which is the raw scores for everybody who took the test in that year. So that's how we're going to do the update, is I start out, if I know nothing about Alice, then I assume that the distribution of her score is just the distribution from everyone who took the test. Now when you tell me her raw score, I'm going to use that to update my belief, and that'll give me the posterior distribution for Alice's value of P. Again, if you look at the code, it should look very familiar because it's exactly what we just did with a coin. We are in some sense treating Alice like a biased coin and estimating the value of P. So if I run satexercise.py, so it prints out Alice's raw score, which is 53. It's out of 54. That's the other crucial piece of information you need. There are 54 questions on the exam. And this is the prior distribution for our belief about Alice. Okay. And now your mission is to do an update for Alice and an update for Bob, and then compare their posterior distributions to see who's likely to be smarter. Okay. If you have questions, I'll come around. In a couple of minutes, I'll put up some hints to help you get started. And we'll see how this goes. If you're making good progress, you can ignore me. If you'd like a hint to get started, you can look up here. So I created a distribution to represent what we know about Alice. And I start out by just getting the prior distribution. So at this point in the code, we don't know anything about Alice, so we just assume that she's a randomly chosen person from the population. What I'm going to do, I'm importing the update function from coin, because the update that I want to do here is exactly the update we were looking at before. The evidence that we've seen is that she got 53 correct and 1 wrong, which we can think of as 53 heads and 1 tails. So we'll do an update, and we'll give it the distribution, which is the prior distribution, and the evidence that we saw. And then when we get the result, we can plot it. And you remember that the prior distribution was kind of spread out between 0 and 1. Now the posterior distribution looks like this, which is we're pretty sure that Alice is smart. Because it's tough to get 53 out of 54 if your probability is less than about 0.8. And in fact, if we had to guess, we would say that it's probably in the high 0.9s, 98%, something like that. Can't be 1, because she got 1 wrong. Yes? The 53 and 1 came from, when you look up the scaled score, it prints the Alice correct part, and it says that she got 53 correct. And then I provided the crucial missing piece of information, which is that there were 54 questions. So I think if you now do the same thing for Bob, he got a 760, and you can find out, by using the same function, you'll find out that that's 52 out of 54. And you can compute the posterior distribution for Bob. Why don't you work on that for a minute, and then we'll figure out the last piece. Hi.
For doing this, you plotted the prior distribution for Alice, right?
Right.
What do you mean by prior distribution there? Because how are you choosing the number?
Right. So it's the prior distribution before I found out what she got on the test. So I used the raw scores from the general population. Because the people who do the SAT, they report that. They tell you everybody's raw score. Yeah, the question is, can you get matplotlib not to block? It does annoying things if you plot multiple plots. You close the first one, it won't show you the second one. It's kind of irritating. One option I'll show you in just a second. You see the function PMF, myplot.pmf. You can also do myplot.pmfs with plural and give it a list of PMF objects, and it'll put them on top of each other. Oops. How are things going? Any questions? Things making some amount of sense? Okay. Yeah. Yep, that's okay. It's just a warning. You should get the picture anyway.
Okay. So
Yeah.
is there a way to specify an output other than a pop-up histogram? Like an output to a GIF or a PNG?
Right. Yes, there is. If you you can take a look at. So when you call that, instead of show equals true, if you give it root equals and then give it a file name. And don't give it a suffix, because it's going to make up the suffixes. There you go. That'll work. And I think by default it creates the ping and the PDF. Yep. It's a fast machine. Hi. Where did what come from?
The evidence come from again?
The evidence is their raw score. So given that he got a 760, we know that he got 52 correct. And that's the output from exam.getRawScore. Again, feel free to ignore me if you're making good progress, but I'll just show you the second part. This is almost the same code we looked at before. I'm going to take Bob's 760. I'm going to look up his raw score, and it'll print that he got 52 correct, which means that he got 2 wrong. And so my evidence is 52 heads and 2 tails, if you like. Same update we saw before. And then this plots the 2 PMFs, one on top of the other. And here's what that looks like. I didn't put labels on these. I could have and should have, but blue is Alice and green is Bob. So we get kind of what we expect here, which is that Bob's curve is shifted a little bit to the left relative to Alice's. Okay. Don't take the vertical axis too seriously. These numbers are, in some sense, arbitrary. They are likelihoods. They're not even really probabilities. So using the green curve, I can kind of tell where the location of that curve is, and similarly for the blue curve, but the heights relative to each other don't really mean very much. So this graph gives us a sense of what the 2 curves are, but it has not yet answered the question we wanted to ask, which is Alice justified by saying that she's smarter than Bob on the basis of this evidence? And so that's the last piece I'd like you to work on. I want to compare those 2 posterior distributions and figure out what's the probability if I take a random value from Alice's posterior distribution that it's higher than a random value from Bob's posterior distribution. And you might remember that we have a function that does that. Sounds right. So the last piece of this, if I've got a distribution for Alice and a distribution for Bob, I can use probbigger, the function we wrote hours and hours ago. And if things go according to plan, you should get an answer that's pretty close to 60%, 61%. So I'll give you a couple minutes to finish that up, and then we'll move on. Did you get 60%? Nice. I don't know how. Okay. Any questions on this exercise? So, if I show these posterior distributions and along with the original, that would show me Alice and Bob relative to everybody else. Correct. Right. And so compared to the general population, we have strong evidence that Alice and Bob are quite smart. But relative to each other, the difference between a 760 and a 780 is quite small. It almost comes down to chance on getting one question correct or not. And so Alice's claim that she's smarter than Bob is only 60% likely, given the evidence that we've just interpreted. Okay. Another way to say that is that there's still a 40% chance that, in fact, Bob is better at answering SAT questions than Alice, or at least as good. Good. Okay. The question was, did we compute the credible intervals as part of the plotting? The answer is we didn't do it, and I forgot that was still in the notes. Did I ask you to do that? Oh, the optional was to compute the credible intervals. Yeah, let me talk about that because it's a good question. So one thing that you might ask when you see those posterior distributions is, what's the range that you think the actual values are likely to be in? And you can compute that with the posterior distributions just by finding the middle part of one of those curves that contains 90% of the probability, likelihood, confidence, however you want to think about it. The reason I didn't put that as an exercise here is that the simplest way to do that is to take those PMFs and convert them to cumulative distribution functions, CDFs. The nice thing about the CDF is you can now ask, well, what's the 5th percentile and what's the 95th percentile? And the space between the 5th and 95th percentile is a 90% credible interval. So if you like, you can take a look at that. Along with pmf.pi, I also provide cdf.pi that does cumulative distribution functions. I didn't talk about that today, but it's a good next thing to think about. If you're doing any work with statistics, get to be friends with CDFs as quickly as you can. It really is very helpful. Most of what I've been talking about today is from Think Stats, which is the textbook that I use in my class. We have ordered copies for everyone. That was supposed to be your handout for today. It turned out, just because of snafu, that we don't have them yet, but you will get email, probably from Stuart Williams, telling you how to get your copy. Your copy will arrive sometime during PyCon, and you'll be able to pick that up. And you can learn all about CDFs there. So that's all the exercises I wanted to do. I have a little bit of wrap-up, and then we'll have some time at the end for questions. And if you want, we can go back and do the Elvis problem, and then we can go get some lunch. So to sum up a couple of things that I'd like you to take away from this, one of them is the framework that we've just done about starting with a prior belief and then doing an update and then having a posterior belief at the end. That's pretty much all there is. When people talk about Bayesian anything, that's what they're talking about. And if you get that concept, everything else is just applying that concept to more and more scenarios. The one thing that changes when you go from one problem to the next is the likelihood function. So if you look at coin.py, you'll see that I split that up into two parts. There's a function called update and a function called likelihood. Update never changes. This function pretty much captures what a Bayesian update is. You're going to loop through all your hypotheses and compute the likelihood of the evidence under each hypothesis. Multiply by that likelihood, and then normalize so that your suite of hypotheses is again a normalized PMF. As you go from problem to problem, that doesn't change. The one thing that does change is the likelihood function. One of the things that I've done here, everything that we've been doing with PMFs, those are probability mass functions, that generalizes to the continuous case, which is a probability density function. Densities are just a little bit harder to work with mathematically. Everything that's a summation, when you do things discretely, becomes an integral when you do them using continuous mathematics. So it's a little bit more of a head scratcher. And then the other thing is when you're writing programs, doing things discretely is easy. So that's where I wanted to start. The one suggestion that I have is if you approach a problem and start out using discrete approximations to it, then there are two possible outcomes. And one of them is that you just get an answer and it's fast enough and it's good enough and you're done. The other possibility is you might find that the problem is getting big enough that it's actually a computational bottleneck. And in that case, there are lots of analytic techniques that you can do. So for example, the coin problem that we did, we chose this discrete distribution of values between 0 and 1. An alternative, if we had started with a beta distribution, then we could do a Bayesian update analytically. In other words, given the number of heads and the number of tails, we can compute the distribution of the posterior just by computing a beta distribution with parameters that depend on the number of heads and tails, which, if you were implementing that, could potentially be much faster. I didn't do a lot of analytic techniques today. My theory is that premature optimization is the root of all evil. That if you don't need the analytic techniques, it's simple and fast, at least for Python programmers, to bang this out. And then you can do the analytic technique to make things go fast. And that's it. We did two things today. I didn't emphasize this point, but we did both an estimation problem and a hypothesis test. So the estimation problem is, what do we think the value of P is? And the answer in that case is either a value or a range of values or a distribution of values. The other is a hypothesis test. So we looked at, is the coin biased or fair? And the answer to that is, I think the probability it's biased is 65% or whatever. Okay? So that's that. A couple of examples I can point you to. So far we've been talking about heads and tails, so you can think of that as discrete data. You can also think of continuous data, anything that you measure. And there's an example that I've written up about estimating the parameter of a decay process. Or you can also think of it as an arrival process. If you stand in a line and you watch people arrive and join the line, you can keep track of what time they arrive. And the probability of a new arrival during any small amount of time is roughly equal, at least under a certain set of assumptions. And you can estimate that parameter. You can take a look at estimate.pi and decay.pi. Those are also described in ThinkStats. So when you get your copy of the book, you can take a look at that. This also generalizes to more than one parameter. So we've been picking on a case like P, the probability of getting heads, or lambda, the arrival rate of an exponential process. Another thing you might want to do is a two-parameter problem. So estimating the mean and variance of a population, for example. And I've got a blog post that I wrote about that you can take a look at. So this is my blog, probably overthinking it, where I pick random problems related to probability and statistics and sometimes other things and write them up. So this was an example where I measured the variability between men and women. I partly did this because there's an old hypothesis called the variability hypothesis that you can read about there. I also did it as a way of talking about summary statistics, that it's not clear when you talk about variability whether you should look at variance or standard deviation or coefficient of variation. And in this case, it matters. And I also did it as an example of Bayesian estimation in 2 dimensions, which is simultaneously estimating the mean and standard deviation. And what you get is a picture that looks like that. So when we were looking at the posterior distributions, that was a one-dimensional thing. And so I showed you a curve that showed the likelihood of any given value. This is the same thing in 2 dimensions. If you read off a height and a standard deviation, this tells you the probability associated with that value. So that's what those contour plots look like. And that's just an example of a 2-dimensional problem. And then the other interesting kind of problem are hierarchical problems. So who's got the recursion shirt? I saw somebody had a shirt. What does your shirt say? Is it? Right. To understand recursion, first you need to understand recursion. To understand, it goes around and around and around. So if you've had some training in computer science, you're used to this idea that once you've learned something, what you tend to do is apply that move at lots of different levels. That's exactly what a hierarchical Bayesian model is. So this is a collaboration I worked on with a colleague of mine in biology, where they take samples from a pond and then grow them under certain conditions. And now they would like to know what the population is of that sample. They know that there are a lot of bacteria in there, and they'd like to know for each species of bacterium, what's the prevalence, what percentage of the population in there. So what they typically do is they take out some ribosomal DNA, RNA, I forget which, send it out for sequencing, and then it gets identified as a particular species of bacterium. And so what they'll get back is, you've got 6 of these, 2 of those, and one of a third kind. Now what you'd like to estimate is, how many species are there in total? And for each of those species, what's the prevalence? So you've seen 3 different species, but it's possible that there are other species in there that you haven't observed. So 3, 4, 5, any of those are possible. So the top level of the Bayesian hierarchy is how many different species are there? And then for each assumption, let's say you know that there are 4, now you can say, okay, so what's the prevalence of those 4 based on the data that I saw? And that's what this article is about. So if you get a chance to read that, you might find it interesting. While I'm here, I'll follow the link to the book. So this is the book you'll be getting. Almost everything I've talked about today has been based on material from chapters 5 and 8 of that book. So if there's anything that you have questions about, you'll have a copy and you'll have a chance to get in there. They should be here now, but they will likely be here today, and you'll get an email about how to get your copy. Good. So those are some things that you can read about by me. I also have a couple of suggestions for books that might be a good follow-up on what we've talked about today. I mentioned Mackay's book, which is where I got the coin example. I also mentioned that that's available free, so you can download that in PDF and read that. The other one, which is in some ways the classic of this area, is Gelman's book, or Gelman and several co-authors. The other book that I have not read yet, but heard good things about, is the Doing Bayesian Data Analysis book. So if any of you read that and want to give me a review, please do, and I'll update these notes, but I think it's worth looking at. That's the dog book, if you've seen the book with the dogs on the cover. Good. The complexity book. So ThinkStats has been out for a little while now. Think Complexity is the new one. And this actually just got released. I think they're going to have copies of it at the exhibits. O'Reilly has a booth, and I think they'll have copies of this. It just came out. So this is the new book I've been working on. It's mostly unrelated to Bayesian statistics, so I won't take a lot of your time to tell you about it, other than that it's a survey of complexity science. There are a set of topics, mostly late 20th century weird science, that have a bunch of philosophic connections between them that I think are interesting, and lend themselves to programming exercises. So the book is a combination of an intermediate level Python book, plus complexity science, plus a little bit of data structures and algorithms. So it's kind of an odd book. If you're interested in it, please check that out. But that's not Bayesian stats, and I promised to talk about Bayesian stats. So, just about ready to finish up, but let's take some questions, and we can. Right, so the question is there a mailing list or a forum for help with ThinkStats? I have a mailing list that I use for my classes when I'm running them, and we could use that, or just send me email. That's a very helpful kind of feedback for me to get, because when I'm working with a class, I know where they get stuck and I can help them. But when you're reading on your own, it's helpful for me to know where you got stuck so I can smooth out that part of the book for the next edition. Yeah. Yes. So the question is, can we get Mackay's book as a PDF? I think if you just Google his name and title, his webpage is the first hit. It's published by Cambridge University Press, but they've allowed him to keep the PDF available for free. Right? So we can have a couple of questions if you have things you want to talk about before we break up. And then we can break. And then if you have individual questions, we can do that. And then the last piece, if you like, how many people would like me to do the Elvis problem or would prefer to do that later on? Elvis? All right, let's do the Elvis problem, and then we'll be done. So if you go back, if you bring up part 1, you can get the statement of the question. Okay. So Elvis Presley had a twin brother who died at birth. That's actually true. We're not making that up. He did. According to the Wikipedia article on twins, I gave you some statistics there about the prevalence of twinning. Now, one of the things that makes, there are kind of two things that make this tricky. It's not obvious how to set up the problem. In other words, should we consider Elvis to be in the general population and then consider the probability of being an identical or fraternal twin. Or we could restrict the population to just twins, and then have only those two hypotheses on the table. It's a little bit simpler and more straightforward to just think about twins. So I laid out two hypotheses. So F is the hypothesis that he's a fraternal twin. I is that he's an identical twin. And the evidence is that he had a twin brother who died at birth. And I can start out with a prior probability, which is if I know nothing about Elvis other than that he's a twin, then I know that the probability that he's an identical twin is about 8%. Okay, and that's the 8% just comes from the data. And now the key piece of all of this is that I need to figure out what's the probability of the evidence if he's a fraternal twin and the probability of the evidence if he's an identical twin. Anybody want to make an attempt at that? Either one? Yes. For identical, it's 1. And for fraternal, it's 0.5. And that's the non-obvious piece that people often struggle with here, is that it's not clear why there's any evidence here at all, except for the fact that he had a twin brother. If he's an identical twin, it has to be a brother because Elvis is male and they're genetically identical. But if it were a fraternal twin, it was possible that he would have had a sister. And so it was actually only a 50-50 shot in that case. So the likelihood ratio is 2 to 1, and that means that this provides evidence in favor of being an identical twin. And then to figure out how much it's in favor, we can apply Bayes' theorem. Although, since you've stuck around this long, I'll show you a little bit of a shorthand. You can plug in the formula that we used before, or often this stuff is a little bit easier to do if you think in terms of odds ratios rather than probabilities. So an alternate form of Bayes' theorem is to say that the ratio of the posteriors is the ratio of the priors times the ratio of the likelihoods. Okay. This comes from just algebra on the formula that we already saw. And just to say it again, because I think it's worth repeating, the ratio of the posteriors is the ratio of the priors times the ratio of the likelihoods. The ratio of the priors in the Elvis problem is 8 to 92. And the likelihood ratio is 2 to 1. So the posterior odds are 16 to 92, which is a little bit less than 16%. It comes out to about 15%. Okay. So you got two things there. One of them is how to set up the Elvis problem and the crucial piece of sneaky information. And the other is the alternate form of Bayes' theorem expressed in terms of odds ratios rather than probabilities. This is often, when you're doing a quick update in your head, this is usually the more convenient form. Good. Any other questions that we should take as a group? The ratio of the likelihoods. Yeah. Question was, what was that last term? And the answer was ratio of the likelihoods. Yep. Question is, what's the difference between this setup and the other setup? Before I wrote out oh, okay. So the terminology here, I said this is the ratio of the two posteriors, and it's the ratio of the priors times the ratio of the likelihoods. Yeah. So what I was doing before was explicitly computing the posterior, well, sorry, the notation is different here and there in a way that's confusing. Let me put that one away very quickly. Let me see if I can, here we go. So when I wrote it out this way, we were explicitly computing the probability of the hypothesis given the evidence. And here we were doing it in a slightly sneaky way by computing the ratio of the two hypotheses rather than just computing one hypothesis. And now to get back to, so now to get the probability of him being an identical twin given the evidence, that'll be my 16 over 16 plus 92. This is how I'm going to get from an odds ratio to a probability. All right. Now that whole thing with odds is just a little sneaky thing that I threw in there at the end. If that makes sense to you, that's great. If not, it's okay. I wasn't really intending to do that carefully. If you really want, we can do that afterwards. Anything else we should discuss as a group before we disband? Very good. I pronounce us disbanded. If you have individual questions, please feel free to stick around. Thank you.